Okay, great. Yeah. So I'm Sam Hadden. I'm a postdoc at CETA. I want to say thank you to Will for doing most of the legwork of the SOC, and to the local organizers. This has been great. I'm having a great time. So I'm going to talk about dynamical production of free-floating planets, or I should really say perhaps not so free-floating. I'll just give you the punchline up front. We know from both long-term radial velocity monitoring as well as microlensing that Jupiter mass planets like our own Jupiter are relatively rare. I think Eve or someone else mentioned this earlier. There are only about 1 in 10 sun-like stars. And as a consequence, the dynamical instabilities of this sort that Sean just talked about may not always produce free-floating planets. They can take much longer. And as a result, there'll be lots of planets expected on wide orbits, but they're not totally kicked out from their system. So this is instability number 3 that Sean just talked about. But just to recap, we think that our own solar system produced a free-floating planet based on its early dynamical evolution. So the story in this latest rendition of the Nice model is that the giant planets form in a compact configuration, pushed together into this configuration due to planet-disk interactions. Then the disk goes away. It's no longer around to damp out the gravitational perturbations. As a result, instability develops rather quickly, and this extra ice giant, this long-lost sibling to Neptune and Uranus, gets chucked out from a close encounter with Jupiter. And it's not crazy to think that this is a somewhat generic situation in planetary systems. In other words, that they form with more planets than they can accommodate stably long-term. You just basically need planet formation to be relatively efficient in order to produce enough planets that they can hang around for about the lifetime of the disk, but after that will perturb each other and result in instabilities. And then, as Sean already discussed, the sort of deciding factor in the fate of an unstable planetary system is set by the Safronov number. So here I'm showing a slightly different variant of the plots we've seen before. This is Safronov number versus orbital period for Jupiter, Neptune, and Uranus, or excuse me, Jupiter, Neptune, and Earth mass planets. And so I put our solar system planets at their current locations around the sun. And you see that the outer planets are sort of squarely in the Safronov number greater than 1 regime, whereas our Earth is down here in the regime where instabilities will essentially ultimately culminate in collisions. That's why we have a moon. We couldn't kick out whatever impacted the Earth to form the moon, so it crashed into us, and now it's there. And you have to move the Earth quite far out in order to get it to be able to eject things. And so one of the things that's exciting about microlensing and moment, especially coming up, is that we're really going to probe an unexplored dynamical regime for low mass planet systems. So now this is my version of the sort of ubiquitous penny plot that we've seen a few times. This is known exoplanets in red and black with some projections for what Raman might detect shown in blue. And what I've put on this plot, or what I've added to it, is the line indicating the locus of points where the Safronov number of planets is 1. So just you adopt some mass radius relationship sort of calibrated to empirical mass measurements in order to make this. But what you see is that for the first time, we're really going to be proposing this region of low mass planets existing where their Safronov number is such that they should lead to ejections. So this is drawn for the assumption of a sun-like host star. But when you additionally factor in or take into account the fact that most stars in our galaxy are lower mass than our sun, with a median mass of about 1/3, this gets even more striking. We'll be probing a lot of planets where they will be ejecting anything they scatter rather than colliding with it. Okay, so back to what I said at the beginning, we already know that Jupiter mass giant planets are relatively rare. We saw in this instability number 3 in the solar system, Jupiter made pretty quick work of the extra ice giant, kicked it right out. But around more typical planetary systems, there's not going to be a Jupiter around. So this is a plot from Suzuki et al. Showing occurrence rates based on analysis of the MOAA 6-year survey, along with a number of data points from different constraints from long-term radial velocity monitoring. And it showed that something like 10% of Sun-like stars host a Jupiter mass planet inside 10 AU. And if you go to lower mass stars, more common types of planetary systems, this occurrence rate gets even smaller for giant mass planets. So in other words, the typical planetary system is not going to have a Jupiter, but will consist of lower mass planets. And the key difference for instabilities in those types of systems is that they take much longer to eject planets. I think Sean already mentioned this as well. But here is hard evidence, if you want. So this is a numerical integration where I've set up a system of 5 Neptune mass planets on initially circular orbits. And you can see they quickly go unstable after a few tens of thousands of orbits and enter into this scattering state. I should say what I'm plotting here. So the bold lines are the semi-major axes of each planet. And then this sort of shaded transparent region around them marks the apocenter and pericenter distance. So you can think of the sort of colored bands as the radial extents of each orbit as a function of time. And I should note that I'm measuring time here in terms of the initial orbital period of the inner planet. So if you think about the system, say, forming at 10 AU, going out to 100 million orbits is something like 3 billion years. So that's, you know, a good chunk, if not the entire lifetime of a main sequence star. And so you can see that after entering the scattering phase, you know, it takes tens of million years to kick out one planet, and then after 100 million years, you're left with one planet who's sort of absorbed all the binding energy of the system, with the other planets scattered out to wide orbits that are highly eccentric and still sort of weakly scattering even at the end of the simulation. Okay, so that's one example of a system. You can do this lots of times. So here I'm showing a summary of ensembles of integrations where I've set up similar 5-planet systems. And all I'm doing is recording the average number of bound planets in each ensemble for a given system based on each ensemble as a function of time. And so this black line shows an ensemble of 100 integrations of these 5-planet systems of Neptune mass planets, like the one I showed before. And these other ones are different planet masses increasing as you go to the left. So the highest mass is 30 Neptune masses, which is actually a little bit more massive than Jupiter. So you can see those fly apart pretty quickly and then settle down into a sort of final configuration where you're left with 2 planets, whereas at the low mass and even after 100 million orbits, you still on average have something like 3 bound planets left. And then of course you could imagine extrapolating this to even lower masses. Ejections would take even longer. I should say that these numerical integrations are very expensive because you have lots of close encounters and highly eccentric orbits. That's sort of a numericist nightmare for doing dynamics. So these took about a couple months or something to run. And so if you look at where these wide scattered out planets are found, there's something like 10 to 100 times further out than when they formed. So if you're forming things at 10 AU, you're going to be kicking them out to hundreds or thousands of astronomical units where you would not see them as bound planets in a microlensing survey. So here's just the cumulative distribution of the expected projected separation measured in units of the initial semi-major axis. So this, I go at the end of the simulation and just look at what's left bound. I exclude the closest in planet that's absorbed all the binding energy. And you see that they're basically flat between 10 and 100 times their initial separation. Another important feature that comes out of these sorts of simulations is that these scattering planets can undergo very close perihelion passages. So it's sort of isolated this region here where this inner planet that's absorbed all the binding energy occasionally takes these really deep perihelion dives, even off the scale of what I'm plotting here. And if you go and look at the simulation results, you find that the lower mass the planets are, the closer pericenter passages they'll experience over the course of this evolution. So what I've done here is gone to each of these ensembles, recorded the minimum pericenter distance that occurred in this 100 million orbit integrations, and this is the cumulative distribution. So you see that in low mass systems, there will be extremely close pericenter passages. So close, in fact, that for any sort of reasonable starting semi-major axis, you would nominally expect that these planets would fall into the star. So this line here, I've marked as the location where, if you started things at 10 AU, that would come within a solar radius. So I've kept these simulations as simple as possible. These are basically just point masses. So I haven't given anything any physical extent, but in a real system where stars have actual sizes, you would expect to maybe dump things onto the star. Another interesting thing to keep in mind is that we know that sort of sub-Neptune systems of sub-Neptunes that are around 0.1 AU are fairly common around sun-like stars as well. And if you're throwing planets from further out, they might disrupt those sorts of systems. So, learning about the occurrence rate and how often these sorts of instabilities happen around sun-like stars will also tell us about what sort of consequences they might have for closer in systems. So I think there's lots to be learned as we probe the population of far out and free-floating planets that have implications for how we think about closer in systems forming as well. Another point to make is that we've seen already from ground-based microlensing that there appears to be this very large population of free-floating planets. Maybe it's just the occasional system with Jupiters tosses out a large number of planets as well to create free-floating planets. So if you take a system with a Jupiter-mass planet and 10 Neptunes, you'll find that the Jupiter kicks out most of them, but on their way out, a handful of them can get stuck at large semi-major axes, and their mutual gravitational perturbations can lift pericenters so that the scattering Neptune mass planets sort of decouple from the Jupiter mass planet and stop scattering, or at least scattering as quickly. And so you even end up with lots of wide separation, but not unbound planets. And if you run an ensemble of integrations like this, you find after 100 million orbits, the average number of bound planets, something like 4. Okay, so that leads me to my conclusions. So as I've mentioned, Roman will be probing a sort of new dynamical regime for low mass planets. It'll be looking at in addition to the free-floating planet discoveries, it'll tell us about the sort of mass distribution or mass function of planets that did the kicking out of those free-floating planets. We already know that Jupiter mass planets are relatively rare, and based on this mass function, if typical systems are comprised of relatively low mass planets, it means that the sort of instabilities that would produce free-floating planets can take billions of years or more to actually eject anything. So many of these apparent free-floating planets are probably wide separation planets. And in the course of these dynamics, these systems can develop really large eccentricities that can have implications for other planets in the system as well. And that's it.
All right, any questions for Sam?
Okay. Great talk. Just on that first takeaway, can you just speak a little bit more on sort of confirming that some of these Roman systems are truly the systems that host a planet that did the kicking?
I guess, yeah, in any individual system, one is not able to say, but
At a statistical level.
at a statistical level, right? So if you go out and find that the number of planets per star, say above a Neptune mass, is at these distances is pretty paltry, then that means there's not enough planets around to make a significant number of free floating planets, even in a billion years. And so that means the apparently free floating planets that you're observing are probably things that were scattered by lower mass things to wide orbits, but not necessarily unbound.
Other questions? So, sorry, is there a question? Yeah, go for it.
So, in those simulations where it takes a long time for something to become fully stable, I wonder a bit on whether this depends sort of on what the initial planet mass distribution is on planetary system. But thinking if there's a wide range of possible planet masses in one system, then might have a broader frequency spectrum in there, therefore sort of a broader spectrum of instability times, whereas if they're all the same, it might be more expensive also.
So I think you're never going to eject planets faster than if you wait. So if I had a wide range of planets, basically you'll be dominated by the most massive planet kicking things out. So I think, yeah, it'll take longer if you, but you're basically, the time scale is limited by the most massive thing. It's the simple way to put it. I wouldn't expect any sort of order of magnitude variations from having a little bit of diversity in the planet mass distribution. We know, for example, Neptune, we have a scattered disk because Neptune takes forever to kick things out. So it's still hanging around. So those are things that are dynamically decoupled from everything but Neptune, basically. And, it's been 5 billion years and they're still hanging around.
So I'm wondering if you compare the equal mass scenarios that you run, basically like 5 Neptune planetary system, and compare this system to the system with the Jupiter, like one Jupiter and a bunch of Neptune. So how does adding a Jupiter mass planet change the ejection efficiency of the planets?
The ejection
rate.
Oh, so not sure I fully understand, but Jupiter is much more efficient at kicking things out.
I mean, say like if you have let's say 5 Neptune scatter each other.
Yeah.
Like what's the typical ejection rate? Like how many Neptune will eventually be ejected?
So based on this, so if you look at the higher mass ones, they're sort of flattened out at 2. And if you go and look at what those systems are like, they're sort of in hierarchical configurations, and you can look at the total angular momentum deficit that the system has, and it's not enough for the orbits to ever cross. So they're basically stuck in this 2-planet configuration. So my strong suspicion is that everything eventually settles down to 2 planets. You just run out of CPU time to get this set of Neptunes or anything less massive to that state. So I think that's the sort of ultimate end configuration. And then
Yeah, but this process will take probably billions of years.
that's right. Yeah. So that's what I'm saying. Yeah.
All right, we should probably move on then. But let's thank Sam.
I think
again.
Sean.
Oh, sorry.
So, yeah, I guess you can't see anything. I just had a quick question. So, do I understand right that you were calculating kind of the closest pericenter distance, but not allowing planets to actually hit the star?
That's right. So nothing has any physical size. And so what would happen probably in reality is that you would dump this inner, so it's usually this innermost planet that takes the closest pericenter passages. And so if that crashes into the star, that's sort of the main scatterer that is around to encounter these other things. So these other sort of scattered out planets come back to pericenter and sort of get a kick from the one that's still hanging around. And so if it's gone, they're going to stop scattering and basically it just gets stranded.
Okay. So do you feel like does that artificially lengthen the duration of the instability center?
Well, so I think everything that's left around is still on these sort of crossing, highly inclined orbits and would continue to evolve slowly and be unstable in the sense that the semi-major axes would change over time, sort of quasi-randomly. But I think everything would just slow down a lot.
So let's thank Sam again then.